welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg, almost always, sometimes also Europe, but today it is Luxembourg. And as usual, we are powered by Research Luxembourg and recording at the studio of the Media Center of the University of Luxembourg. And in today's show, our guest is Dr. Alexandros Gerakis, Senior Research and Technology Associate at LEAST and Adjunct Professor at Texas A&M University at the Department of Aerospace Engineering. Alexandros' interests include laser, plasma, and laser matter interaction, nonlinear optics, photonics, and gas flow measurements. Alexandros, thank you so much for coming.
It's a great pleasure for me to be here.
When I was preparing for the show, I just noticed that, we always strive for the balance of the topics, of the institutions and everything. And we made one serious mistake. And you know what it could be?
LEAST was not included.
No. We keep having researchers whose first name is Alexandros. We have really, I think, already 4 or 5 people like that. I don't know whether it comes kind of with the name comes the research part.
It is a great name.
For sure, I have to say that my son is named like that. So Hopefully I see a great future for him.
Oh, fantastic.
Okay, good. But of course, let's focus not on your name, but on the science that you're doing. And I actually wanted to take you a couple of years back. Mm-hmm. So I found the title of your PhD thesis at UCL. And just, because we will focus a lot on plasma today, on neutral gas flow and things like that. But I just also decided that there is one term that I don't know about and I would like to know because I noticed you did publish a few things about it. These are optical lattices. Because in your PhD, you were writing about controlling and probing molecular motion with optical lattices. Mm-hmm. And this is something I have no clue about. So let's start with optical lattices.
All right, yeah. I did my PhD at University College London in the UK, of course, at the Department of Physics there. So my PhD research had little to do with what I'm doing today. The original plan was to use these optical lattices, and I will explain what that is, to control the motion of hydrogen molecules. That means, if we think about it in simple terms, right? If we say that something has a temperature of 100, whatever units you want to use, that means that it has some energy and it moves around like that. If then this cools down, it means that it doesn't move a lot around its center position. So then if you stop something completely, then practically you're cooling it down completely. And if you cool it down completely, then you can actually study. That was the overall project. So the idea was to actually slow down, i.e. just cool down hydrogen molecules, which could then be studied for astrophysical reasons or for whatever reasons. Cold atoms was the exact same case, and that won the Nobel Prize in 92 or 93, if I remember correctly. And then the next step is to do the same thing with molecules. So unfortunately, to this day, this is a 20, 30-year-long effort that is not there yet. But anyways, that was my PhD project. Now, during my PhD project, which was using optical lattices, I also happened to develop some diagnostics for gas flows. And these were there before that, before I studied them. But they had a problem that they weren't fast enough. They were diagnostics for gas flows, but they would take like 10, 20 minutes for a measurement to be made. That means that, if you want to measure your temperature, you'd have to wait for 10, 20 minutes to measure it. And of course, we much prefer it now where you can do it in a single shot. So then I did manage to get those measurements within a single laser shot. So from 10 minutes to some nanoseconds. So that was big, and I decided that there is a great research opportunity there, and this is what I'm doing to this day. Now, what are optical lattices? So we can think of light like waves. The exact same way, so I don't know if you go to the gym and you have the ropes, right? And you do the thing with the ropes up and down. You can think of light doing the exact same thing. It's extremely equivalent. So light goes up and down as well. Now, if you take 2 of these ropes hitting the exact same spot together, depending on the relative phase, by relative phase, if you tell the rope to go up at the same time as you tell the other rope to go up, then they would go twice up. However, if you tell the rope to go down while you tell the other rope to go up and they meet in the center, then they wouldn't go anywhere. That's called interference. So you have positive constructive interference when you add the 2 phases, or constructive interference when they are in antiphase. So when you take then 2 laser beams, you can do that with a laser pointer. You take your 2 laser beams and then you split them and then you combine them again, you interfere them, as they say. Then you create areas of light where you have double the initial intensity and areas of light where you have zero the initial intensity. Double, zero, double, zero, double, zero. So if you do this in vacuum, then you have just light, nothing else. However, if you do this in atmosphere, and we do this in my lab all the time, where we just do it in air, you interfere two laser beams, two intense laser beams in air, then oxygens and nitrogens that are in air are seeing this high, low, high, low, high, low. And due to what's called the optical dipole force, that means that the light is actually exerting some force on these particles. So these particles feeling an attraction towards the high regions of that interference pattern. So if you add interference pattern and molecules or atoms, then you create what's called optical lattice. And that is a periodic density modulation that you have introduced in the medium where you are doing this. And then what you can do from that is you can use these for various diagnostics, but also manipulation of matter. So these are generally the areas where we're working.
Wow, that was a long description, right. But I could follow. Thank you so much. I mean, especially the rope parts really, made
I think the ropes help in describing these
Totally,
waves.
Totally. It's a very good idea to do that. But you mentioned the lab, actually, and the lasers that you're using. Mm-hmm. I find really, when you say lasers, when you say plasma, that we will be discussing later on, these are really terms that have very, very good PR. People are always like, wow, lasers, right?
Lasers, with the quote from the Austin Powers.
Yeah. Exactly. Or lasers, I already think, Star Wars or whatever, right? The laser sabers or whatever, right? It's cool. So how cool is your lab? I mean, if I were to visit it.
You have to ask my students and postdocs that, but I think it's a pretty cool lab. First of all, there is a rule that music has to always be on. So we always work with music. I don't always agree with the music that plays. So sometimes some of my students like K-pop, and I'm not a big fan of that, but okay. But generally, no, the lasers we're using, and especially since we upgrade them, I mean, they're very powerful. Usual demonstration is just, we can break down air pretty easily. Or, if a piece of dust happens to be in the vicinity, then suddenly you hear a boom. But that's just the dust being broken down. And overall, I think, we do cool stuff. We're definitely the only lab in the globe that is doing this type of research to this day. So our lasers are unique, and they are unique because we design them, we build them, we commission them, and the whole thing is like that. I mean, currently the lasers that we have are relatively lab scale, so they're pretty big. And, it's like, imagine if you're building a car, imagine a car where you just start building the engine, so you don't care about, the color and stuff. So we are at that stage where the engine is exposed. But now, actually, we, through my Attract as well, we are funded to create the next generation of these lasers. So we're now creating newer, smaller, more versatile laser sources for that. So overall, I think it's a cool lab. I mean, we have wind tunnel in my lab. We have big plasma chambers. We have 3D printers. We have a variety of lasers. And I think it's a pretty nice lab.
Makes me think that the next time there's a chance to visit LIST labs, because there are chances, yes. It's sometimes open for the general public. Absolutely, listeners, do go and see it. Because I haven't. I've only seen the coating lab, where different coatings are applied. And one of the obviously big problems was that it was impossible to talk inside because it's very, very loud, right? So I guess we're not talking about...
No. You can definitely talk inside there unless the music is too loud. But I mean, apart from
that...
If
you're able to put music on, then most probably it's just louder than the noise of the lab. Okay, so we know it's cool, but then why? Why the lasers?
Why lasers? I mean, I don't know. To be honest, when I was a student, I always knew I wanted to become a physicist. So when I was 14, I had decided I'm going to become a physicist. I didn't know what I liked in physics, but I liked physics generally. And then in the first class I had in the third year of lasers, in the first hour, I was like, okay, this is it. For some reason, I don't know, it clicked. And I've been doing that ever since. And my master's was in photonics and laser development. And then my PhD was that. And then I've been working with lasers ever since. I don't know. I mean, for some reason, I like lasers. They are cool. To me, they're not hard to understand. So that also means that I have, maybe some better understanding there. Also, it's something that unfortunately is not... And when I'm talking about lasers, I'm talking about laser development. Practically, research stops to what the companies can give you these days. we're taking a step further and we're like, okay, we're not going to wait for that. We're going to create the lasers we want. And unfortunately, this is a dying art. I really hope it changes. But I mean, from a funding level and from a research level, this is working great for us. So lasers are cool. I've never had a dull moment working with lasers. So yeah.
So what are they actually? Maybe we should say, because you said you find it interesting and simple to talk about. So.
Yeah, I mean, so first of all, the important thing to say here is that laser was invented, was not discovered. And the difference is that to be discovered, it has to already have been there, and we just opened up a hole and we found it. But invented means we made it from scratch. Because, the laser has a very unique light. Just looking at it is cool. And then the fact that you can manipulate matter using this light, then this is also super fascinating. So what is a laser? Okay, that's interesting. So, if you see a lamp, a fluorescent lamp, or the light from the sun, this is light just going in all phases, going everywhere and doing nothing, right? So then I think it was mid-1910s, Einstein came up with the idea of, hey, let's try to put some order into that light. Let's put one photon right next to the other, and then they would come up with a third one, blah, blah, blah. And that was, in the 10s. Then in the 1950s, I think 1956, the maser was invented. Maser starts first, and I keep on making parentheses. So laser starts, it's not an actual word. It's an acronym. It starts for light amplification by stimulated emission of radiation. Now, masers is microwave amplification by stimulated emission of radiation, and they were invented first in 1950s. But of course, these were with microwaves. And then people realized, okay, if maser works, laser should work as well. And then there was a global race. And Teddy Mayman invented them in 1960s in Hughes Labs in California. So what they are is actually you are putting all the photons, rather than being randomly scattered, anti-phase, whichever phase. You can think about it like the following. So you can think of the Soviet army, where, all the soldiers work with exactly the same marching, looking at exactly the same area and stuff. This is a laser. All the photons do the exact same thing at all the time. That's called coherent light. And then you have the coherence time, which means practically, when will these soldiers get bored of doing the exact same thing all the time? And then you have coherence length, blah, blah, blah. So that's what the laser is. And then that allows us as researchers to be like, okay, I have a source that is I can predict. And if I can predict it, I can control it. And then everything follows. But this is what's unique about lasers.
And then if you can predict it and you can control it, you can have applications.
Yes.
And what about applications in your lab? What are you using lasers for?
So, when the laser was invented, it was termed a solution looking for problems. So initially people didn't know lasers were cooled. Dr. No was 1964. So only 4 years after, Dr. No tried to kill James Bond with a laser in that scene. But people initially didn't know what to use a laser for, apart from killing James Bond.
Which is sometimes maybe very useful for the villains,
sure,
at least.
Yes, if you're a villain, sure. Or, Star Wars and stuff. So applications, nowadays, even the internet is the application that stands out more, barcodes and all these things. But also in science, LASIK, we should not forget about how, you have medical procedures now based on lasers and stuff. In our case, we are using lasers mainly for diagnostics for the moment. So what do I mean for diagnostics? So, when you have a thermometer and you put it in your forehead to measure your temperature, what you're measuring then is not actually your temperature, is the interaction between your temperature and the temperature of the thermometer. They cross-talk a bit. So what you're measuring in the end is not your actual temperature, but it's actually an inferred temperature from that interaction. So that's called a perturbative measurement. Or, if I lick my finger and I put it in a flow and I try to see where the flow goes, that's a perturbative measurement because I stick my finger in there. And this is mainly the way people, to this day, they use perturbative probes to diagnose neutral flows. And by neutral flows, I'm talking, the flow around the wing of an aircraft, hypersonic flights, plasmas, all these things. They're using perturbative probes to do this, to perform these measurements. So which means that then the measurements are not accurate. If you don't have accurate measurements, then you cannot design better whatever it is you want to do. And this is where we come in. And we're like, okay, you know what? We have this tool, and this is a unique tool globally, and we can actually perform all these measurements without perturbing anything that we're measuring. And then we are expanding that application range, and we're demonstrating to the world that we can do these things. And already we have had great interest in it.
So we're talking laser diagnostics.
Laser diagnostics, yes, exactly. Laser diagnostics for neutral gas flow, that means exactly the flow above the wing of an airplane, or plasma diagnostics, where we are talking now about the fourth state of matter, where things are a bit, not as advanced as we would like them to be.
Before we move on to not as advanced as we would like them to be, and plasma as such, I think it's the right moment to look at the pub quiz question that we normally ask in the beginning of the show. And listeners, remember, as usual, the question is now, but the answer only at the end of the podcast. And it's a very surprising question, I think.
Yeah, so the question now is, at the backyard of which Nobel laureate was I fixing my car?
Great question. Of course, I'm very excited about it because you can't Google the answer, I guess. I don't think you... Did you publish it somewhere on the internet?
No, I think it's the first time I disclosed it.
Okay, good. So, listeners, remember, answer only at the end. And now we're moving on to plasma, as I said. Mm-hmm. So, you said that lasers were invented, but plasma was discovered, right? I guess.
Correct. I mean, do you know what's the biggest plasma everyone knows?
No.
The sun.
True. No, I was just thinking that plasma in general is like, what, 90% of the...
99%.
99%. Of the universe, exactly. So I was thinking universe, but I don't know whether that would be the right answer, right?
No, 99% of the universe is indeed plasma. I mean, the sun is a big plasma chamber itself.
And it's a fascinating thing to discuss because it really gets people excited, at least it does for me, right? And also it's one of those things, when you have science shows, you always get a...
plasma ball.
Exactly. And then, you can touch it. It's all cool. And actually we have one also in the Science Center in Differdange, if you want to see. You can go there, but also some scientists, also at least at ESRIC, I know they research also plasma, and sometimes they come to different shows, so you can check for yourself. But first of all, a classic question. I know you're not responsible for the school curriculum, but I always wonder, you go to school and certain knowledge gets updated, but certain is not. And when we talk about the states of matter at school, it's only 3, right?
Yeah. And
plasma is the 4th one.
Plasma is indeed the 4th one. And that's not the Luxembourg problem. I was recently at a conference in the US, at an APS conference, American Physical Society, where it was also, at the one about policies and stuff, it was also mentioned that in the US as well, plasma is not mentioned. I think only 2 states out of 50 have plasma in the curriculum. To be honest, I'm not entirely sure why. Plasma, out of all the 3 states of matter, is not in the classic curriculum in the sense that it was even termed plasma in 1920s by Irving Langmuir. And by the way, being Greek myself, plasma in Greek is used in a completely different context than plasma. So Irving Langmuir called it plasma because it reminded him of the blood plasma. But actually, in Greek, plasma you would use to call something a creature. So creature is a plasma. See, you didn't know that.
No, of course. I don't speak Greek yet.
So anyways, so I can understand. And also our knowledge about plasmas is not as advanced as is solid state physics or quantum or whatever.
Really? So we know more about quantum than about plasma?
100%.
Okay.
For historical reason, for funding reason, because we don't know how to tame it. Now there is a huge need for understanding plasma for 2 main reasons. First one is what's called low temperature plasma, where you use plasma for nanofabrication, silicon, everything. Every chip is actually made in a plasma chamber. So you do need plasma. And since now we're pushing that technology, the more we understand plasma, the better we can utilize the technology. And believe you me, we have no clue about most of processes in there. Second one is fusion plasma. And fusion plasma is something that over the last 2-3 years has been huge, and it should be huge because once solved, it's going to solve the energy crisis globally forever. But there again, there is a ton of unknown stuff, and there's a ton of money being pumped currently, but there's a big lack in our understanding about the processes there as well.
So fusion plasma, is that related to nuclear fusion, or that's a different process?
Nuclear fusion, yeah. The bad thing with calling it nuclear fusion is that people would confuse it with nuclear fission, and that should not be done. Nuclear fission means you break a thing in two, and nuclear fusion is you collide two things together. And the one is harmless and the other one is harmful. So that's why I said fusion, because I prefer just saying fusion energy. I think it's a less confusing term, and it's one that should stand out.
But it is related. It's
the same thing.
Yeah, okay, it's just true. Yeah,
but I remember, it's how you market things sometimes. And,
of course. I remember I was watching. There is this competition for young scientists here in Luxembourg, young Forscher, and there was actually one competitor who was talking both about fusion and fission, and I was really impressed that she was never getting it wrong, because it is really such a similar term.
Exactly. That's why I said fusion energy and not nuclear fusion. Exactly for that reason.
Okay, good. So we know that plasma is there, as we said, 99% of the universe. You said so many production is now applying plasma, but we don't know much about it. So what do we know? What is it actually, except for being this fourth state?
Okay, so the states of matter have to do with the temperature, we said earlier, right? So temperature means how fast or not particles are moving. So if we are thinking of a solid, things are not moving very much. That's why they collide together and they stick together and they're best friends forever, and that's it. Now, if you turn up the temperature a bit, then, some of these bonds are going to start breaking because things are starting to move a bit faster. And then solids would turn into liquids. You can think of an ice cube turning into liquid water. But then if you crank up the temperature even further, then these bonds are going to break even more. So then liquid is going to turn into gas. So again, if we think ice cube turns into liquid and then it turns into water vapor. But now if we take the temperature even further, now what happens is, if we all remember from school, you have the nucleus and the electrons around it. Now you break even that bond. So instead of having a neutral particle where the electrons are moving around the nucleus, now the electron is stripped out of there and they're free to move. So you have positive charges and negative charges all in a soup, along with some neutrals there. So suddenly you have electrons, ions, and neutrals being all together. And that's what plasma is.
And then what do you do with it? I mean, what is the interest for us?
Okay.
That's a long subject, right?
I need to think about that. So because they're charged, now that means that you can apply electric fields to control them. For example, right? So you can take the ions and use electrostatic lenses to move the ions and use them, for example, for mass spectroscopy, which we do in LIST. You can use the electrons and do other processes. You can do lithography, for example, as well. Or since you can then have all these particles, moving at very high temperatures together, if we're thinking about fusion energy, then that means that you have a finite chance for two protons to collide together and to fuse together to create a new particle, right? From which you release energy and then you can use it to boil water. So, applications are really vast and numerous. There's plasma medicine these days, there's plasma agriculture. So I have colleagues at Stanford who use plasma to activate water, to replace nitride, soil things. The word is escaping me now. Of course, you have another area, for example, that we need to think about is space. So if you have the re-entry of a vehicle in an atmosphere, in Earth's atmosphere, then the friction between the vehicle and the atmosphere is so big that then you have plasma created there. Of course, you need to diagnose that and to see how that goes in order to create better vehicles and, protect the astronauts and what have you.
Not mentioning the problem with the communication, right?
There's the blackout as well.
Exactly, moments of terror, right?
Yes, exactly. So, this is also very actively researched these days. There's also, the physics of plasmas. It's not understood, how things are doing. We have a very recent publication by my student Gabriel, where the optical lattices that I was discussing earlier, for the first time we did a Gedanke, a theoretical experiment, where we were like, okay, what if we shine those optical lattices into this soup of particles. And we are the first ones ever to have studied this problem because, it's not trivial, and it was not an easy paper at all. I should also mention applications coatings, as you mentioned as well. We also do it in LIST. We have a whole group where we use plasmas for coatings of everything. Plasmas have really, really a lot of applications, but the more we understand them, the better we can utilize them.
So there's what I see a lot of, energy applications, right? So getting this idea of constant flow of energy, whatever. But there is also the problem that you have to put a lot of energy in order to actually create the plasma, right?
I mean, that's the holy grail with fusion, what's called rich in ignition. And that's what was showcased in the National Ignition Facility in Lawrence Livermore 2 years ago, where they managed actually to get more energy out for the energy they put in. And that was the first time this was showcased 2 years ago or 3 years ago, I don't remember. But once we managed to do that in a sustainable fashion, then we will have free energy forever. And that's a big application there.
One of the holy grails with plasma.
One of the holy grails for sure.
I wonder why not all the researchers are doing plasma research. It sounds really like a great field.
I mean, what we say in research, you go where the money is, right? So, for example, for up to now, all of the money for research was going for combustion. We all know that this has an expiration date. So now, and with the green energy, it looks like, of course, there is a lot of research in green energy as well, but it looks like it's not cutting it the way we would have wanted it. So now people are like, okay, what is then the thing to do? And this has actually sparked a lot of enthusiasm in the scientific community, working in fusion, because it's a great problem. It's a big problem for mankind, and people are very committed to it. So I think it's something great.
For sure. Going back to when you were explaining, the fourth state of matter, and you said, okay, from gas we turn into plasma. Can any gas become plasma?
Yeah, practically. Yeah. I mean, I'm trying to think. I think yes. As long as, every particle has a nucleus and electrons around it, just removing one electron immediately turns into the ionized state, and that would then be plasma.
And you're getting different qualities then of that plasma.
Yeah. I mean, you have, for example, degrees of ionization, which means out of the 100 particles you have there, how many did you ionize? So 2% means that only 2 are ionized. And you can use them for different applications depending on that degree, for example. Then you have temperature. So temperature means, again, more energetic. Then, if you want to do lithography where you penetrate further into the substrate, then you need to increase the temperature, and stuff like that.
What kind of temperature do you need actually for the gas to turn into plasma?
That is species specific, and it has to do with how much energy you need to give to that particle to strip one electron out. And that is species dependent. So, I cannot give you a
Sure. Well, I was also wondering, okay, so let's say we have plasma and you just keep increasing the temperature.
Just give you an idea. I just thought, lighter, fire is also plasma, right?
No.
Yes.
Okay.
So there you also have that. So that gives you an idea as well.
Yes, it does.
Very low ionized plasma,
but still, okay. Never thought about it this way. Mm-hmm. Very inspiring.
Look at the sun.
Yeah, okay.
The sun is a big fireball, right?
True, absolutely. I was just wondering, so when we're talking about those temperatures, all right, it depends on what type of gas we're talking and the situation of the electrons. But then what if you just keep increasing the temperature? Do you get a fifth state of matter? Or?
I mean, then the electrons are indivisible. So there's that. I mean, but then you're talking about nuclear stuff because then you're going to break the bonds between the protons and the neutrons, and you have other physics in play there. So, yeah.
And do then the particles collide more or not with the increase of temperature?
So you have an interplay of forces there because you have the kinetic energy, which is the temperature, which means, you can think of the balls in billiards. So the more energy you have these billiards moving around more. But then on top of that, you have Coulomb repulsion, because now you have charges. So as we know, the opposites attract, but the same charges are opposing each other. So then it's a complicated problem. But there are collisions for sure, but then because there's an interplay between the kinetic energy of the particles and the Coulomb repulsion. So you have to estimate this.
Okay, it reminds me, I was recently listening to a very fascinating podcast. I would actually tell our listeners to go and listen to it, but it's in Polish. So only for the Polish listeners, there's an amazing science podcast. And there was a physicist talking, of course, about dark matter and dark energy and exactly, the cosmological constant and the problem of repulsion and how to really define it. So, just if you're interested in that and to know more little about dark matter and energy, and you speak Polish, I'm going to share the podcast in the show notes. Okay, whoa, we've gone through so many different things, and I'm trying not to over-jargon our discussion, but the problem is I always have this problem that when I prepare for the podcast, I read a lot of articles that my guest published, and it always starts with the title, and then the abstract, and then,
I don't really like the titles of my paper.
Why not?
Because they're extremely long.
They're extremely long, and they're using a lot of difficult terminology. And I know they have to because these are methods that you're applying, right? So it's important. But there's a lot of different terms with scattering. And I have to ask that, like, what is this scattering? And there are so many people that looked at the scattering. We have Rayleigh and Thomson and Brillouin. Okay, I don't even know.
French,
Yes, exactly. It's even very difficult name to pronounce for the foreigners, right? So
what is scattering? So scattering is... scattering is just, you can think of scattering again. Billiards is when you send in one ball and hits the other, that's scattering. Now, you have different ways of scattering things from things. So you can have X-ray scattering. So that means that you take X-rays, you shine them on something, they're being scattered. That means the X-ray is hitting an atom there, and it's been, thrown or scattered somewhere else. That's scattering. You have light scattering. Practically, so the way we see is actually scattering. So you have the light, photons coming out of the lamp, hitting something, then that light is being scattered and it reaches our eyes. That's how we see it, through scattering. So that's oversimplifying it, but it's not inaccurate. Then we use scattering to learn about things. So the same way we use the light scattering to learn about the shape of this table in front of us, we can use the same principle to read about things. So you use the X-rays to read about the crystalline structure and material. In our case, we use photons from the laser to be scattered from the oxygens and nitrogens, as I said before, in order to then read their temperature. And we do that just by using light, without having to use, a thermometer and mercury and all these things in there. So that's what scattering is. And then different scattering mechanisms have been historically discovered by different people. So Rayleigh was the one who explained scattering of light by neutral particles. And that explains why the sky is blue. Do you know that?
No.
All right. So what Rayleigh found is that there is a lambda to the -4 relation, lambda being the wavelength of light, of the scattering process. That means that if we think of the visible spectrum, where blue has a shorter wavelength than the red, which has a higher wavelength, then that means that blue, in general, is being scattered much more than the red. So then what that means is that if you have the light from the sun going through the atmosphere has oxygens and nitrogens, those photons are being scattered by oxygens and nitrogens. The blue photons are scattered much more effectively than the red photons. And voila, blue sky.
But then with sunset and...
Sunset, right? Fantastic. So in sunset, then you have, because if you have to think of the relative position of the sun and the earth. So during daylight, the sun is right above you, so there is small thickness of the atmosphere. But then during the sunset, the thickness of the atmosphere that light goes through is much thicker, right? Because you go on a tangent. That means that until light reaches your detectors, and your detectors is your eyes, all the blue has been scattered, and all that's left is the red. So that's why, and if you think about it, when you look at the sunset and you look at the horizon, you see dégradé in French, from light red to high red. And that's because of that. It's different thicknesses of atmosphere, and then that's why you have.
Really interesting. I actually recently also heard a discussion about the color of the clouds.
That's different.
Okay.
I don't know about the color of the clouds, but then you have red atmosphere also when you have a volcano eruption. But that's me scattering, which is scattering of light from particles, from larger particles. It's also red, and people confuse the two, but it's actually different scattering mechanism.
Okay, so it's not Rayleigh anymore.
Not Rayleigh anymore. Then it's me.
Okay, so we kind of explained a little bit. If you want to know more, of course, go read up on it, because I think it's getting very, very technical and I still want people to be around somewhere here. But very, very interesting. And I'm happy, when I said scattering, I noticed that you consciously used a lot of the verb scatter to show this is scattering, that is scattering. So that explains a lot. Just to wrap up, sometimes in our show, I have guests who actually have quite a few patents. And just like articles, when I look at the applications of the patents, I don't always understand what is so special about them. So I just wanted to ask you, what have you come up with? What are the patents that you have applied for?
I currently have two US patents granted. I have one European or global patent pending, submitting two more. So the granted ones, the first one is actually to be used in ITER. ITER is the large fusion reactor in Cadarache in France. So there, because the vessel is going to shake, and when you are sending in laser beams through various mirrors, the whole thing shakes, and then that means that your whole laser is shaking, and then you are losing your alignment. So then while I was at Princeton, we devised a mechanism that would keep the alignment no matter what. So that was a patent there. Another patent that was recently granted was with some novel mechanisms to distinguish our Thomson scattering. Thomson scattering is scattering of light from electrons and making the whole process better overall. So, yeah.
Okay, good.
And I am also submitting some. We have some patents on laser designing and these types of things.
So watch this space for sure. And congratulations, of course. I don't have any patents. Maybe one day I should change the job first of all, of course. Obviously, I don't think you can get patents with just podcasting, just in inverted commas. But, as I already hinted to it, we're kind of slowly wrapping up. So what remains is to look at the pub quiz question that you asked in the beginning. So if you can remind our listeners what the question was about and then give us the answer.
Yeah, so the question was, at the backyard of which Nobel Prize winner was I fixing my car? And the answer is John Nash, the John Nash from A Beautiful Mind, from the movie. Nobel Prize in economy, I don't remember which year. So the story is that I was, when I was at Princeton Plasma Physics Lab, I was working there, and one of our technicians there, his house and his backyard was neighboring that of John Nash. So this technician was also making some side money by fixing cars in his backyard, and that meant that I was actually fixing my car at the backyard of John Nash, which I had found intriguing at the time, remembering having watched The Beautiful Mind in the movies, in Greece as a kid, and then...
Yes, of course. But you didn't go, just saying, I'm looking at the car, but actually peeking at what's going on.
Because he was already pretty old. I mean, he died like 5 years ago, I think, from a car accident. But he was already pretty old. Also, his mental health was not fantastic still. So his son was there. I had seen his son coming in and out. I think he also had some similar issues. But no, I would not disturb that. But it was his house.
Yes, you're sure about that. And the car was fixed well, I hope.
Yeah, it was all right.
Because that's also an important part, right, of the story. Okay, you mentioned where you were working, so I was just wondering, I assume the lab is still there, the Princeton Plasma Physics Lab. What are they doing right now? So what's the cutting edge? I assume it's cutting edge. I'm not saying that it's not cutting edge in Luxembourg, but I assume there is also something important there going on.
I'm also collaborating a lot with them as well since I was there. So Princeton Plasma Physics Lab, PPPL, started mainly to study fusion. So the largest tokamak is the vessel where you do fusion. In the US, up until recently, was in PPPL. Unfortunately, they have had a downtime over the last 10 years for some technical issues, but they're also growing now low temperature plasmas. And by that, I mean, first of all, they are laser diagnostics. They have laser diagnostics there. Actually, one of my lasers is still there operating.
Not shaking.
Not shaking, no. They collaborate with Samsung, for example, for chips and, types like that for low temperature plasma. So they're starting to diversify a bit and looking into these applications as well.
You mentioned tokamaks, so just to make it a bit clearer. So we have different accelerators, let's say, right? Mm-hmm. And then from that on, you get even bigger chambers and bigger kind of buildings that are tokamaks. And in Europe, how many do we have in Europe?
I can't give you a number. I know, for example, in France, there is West, there is the Demo, there's ITER that's been built, there's SMART in Spain.
There's one in the UK as well, I think, right?
JET was decommissioned.
JET, exactly, but it's decommissioned, yeah.
There is W7X in Germany. I'm 100% certain I'm forgetting others, but yeah, we have in Europe as well.
Just to put it into perspective, because I think it's a subject that is very interesting. As you said, we discuss a lot the fusion technology and whatever, but I don't think we discuss tokamaks enough. So just wanted to say that there's a lot going on, not only in the US, also here in Europe. So I don't know if you can really visit these places. Normally not, probably.
I don't know.
Exactly. But then again, it's I had the chance to visit a few accelerators. And, obviously you can only visit them when they're not working. Yes, so then it's not as interesting, I guess, as actually seeing the research done in them.
I had actually been to CERN in 2007, and it was they were doing the one that made the Higgs particle. And we actually went 100 meters down in Earth, and I think I have a picture somewhere where my face is in that. I have put my whole head into that thing, and it was...
It's a cool place to be, for sure. And not that far away, CERN, if you're interested. Okay, thank you so much, Alexandros, for coming today. It was very, very interesting, and I hope listeners enjoyed it as well. And continue all the good work.
Thank you so much. You should visit us anytime, and people who listen to us should feel free.
Exactly. If ever there are some, free visit days, let me know. I'll tell the listeners
I will
to
totally
go.
Let you know.
Okay, perfect. And this is it for today. Don't forget to subscribe, to follow us, to reach out to us. Remember, we have a brand new website, SciLux.eu, where you can find all the previous episodes. And also, just small reminder that as we are growing a little bit, we're trying to interview European scientists. And that sometimes means that we need some support. So if you want to support us, there are those green buttons you can click. And let's just continue talking about science, Luxembourgish science, science in Luxembourg, and European science as well. This is it. My name is Hanna Siemaszko, and this was SciLux.